Okay, so today we're going to be covering two important theorems, namely the Bolzano-Weierstrass theorem and the nested intervals theorem. And both are pretty important results, but the proofs aren't that long. In fact, I'd say the proof of the existence of a least upper bound is a bit longer. The first one we're going to be covering is the Bolzano-Weierstrass theorem, which says that if x sub n is bounded, right, let x sub n be bounded, so we can say that the absolute value of x sub n is less than some value m, for some m in the real numbers and all n in the natural numbers. Then there is a convergent subsequence x sub n sub k, which converges to some limit L, which is contained in the interval from -m to m. Alright, so we'll start with the proof of this. The main idea here is going to be called, we already sort of saw this in the proof of the existence of the least upper bound. We're going to be using interval halving, right? So in particular, we're going to start with the interval -m to m, right? Because we know that all of the values of x sub n are going to be contained in that interval. So let's say let a sub 1 be -m and b sub 1 equal +m. Thus, x sub n is contained in this interval for all n. And we're going to start our subsequence, x sub n sub 1, as being our first value of the sequence, x sub 1. Now, let, I guess I'll call it C, since we're already using x for the sequence. Let C be the average of A1 and B1. Of course, we know this is equal to 0, but it's not really important that we know it's 0. Then, or I should say, if there are infinitely, my handwriting got sloppy there, infinitely many x sub n in the interval a1 to c, let a2 equal a1 and b sub 2 equal c, right? So what we're saying here is that the new interval is going to be a1c, right? Otherwise, let a2 equal c and b2 equal b1, right? And notice that there have to be infinitely many x sub n in either one of the intervals, which you can prove by contradiction if you assumed that there were finitely many values in both intervals, then there have to be finitely many in the entire interval, but we know that's false because we have the sequence itself is infinite. So if we cut it in half, there has to be infinitely many and at least one. It could be in both, but at least one. We continue indefinitely using, let's say, c equals a sub n plus b sub n over 2, right? So we just keep taking midpoints, and there have to be infinitely many values of x sub n in each of the subintervals. So since our infinitely many values of x sub n in the new interval, say a sub 2, b sub 2, then let n sub 2 be bigger than n sub 1, such that x sub n sub 2 is in this interval. Right? If n sub 2 didn't exist, that would imply that that the only possible values for x sub n being inside of this interval would be 1 through n sub 1, which is finitely many. And of course, n sub 1 equals 1, but you know, we're just speaking in general. That would be a finite amount, and so so we know by the infinitely many x sub n in this interval, we can find some n larger than our initial one. And so this is how we create our subsequence. This creates x sub n sub k. So notice each x sub n sub k is going to be contained in the interval from a sub k to b sub k. Now, the length of these intervals, b sub k minus a sub k, and I'm going to put this in absolute values, even though this is going to be positive, or at least non-negative. I'm still going to put it in absolute values. This is going to be 2m divided by 2 to the n minus 1, or of course I could write this as m over 2 to the n minus 2, right? But the extra 2 here in the top came from the original length of the interval, negative m to m, is 2m, right? And this sequence of lengths, or sorry, this should be a k actually. This sequence of lengths converges to 0, right? Because 2 to the k is going to grow without bound, and then if we divide by that, it's going to go to 0. Of course, that is an informal argument, and you should prove it rigorously. Now let epsilon be greater than 0. We are going to use the this limit definition, the epsilon n definition. Thus, there is n in the natural numbers such that if n is greater than n, or greater than equal to, then b sub n minus a sub n is less than epsilon. If I and j, or let me use j and k, are both greater than or equal to n, let me think. Okay, so x sub n sub j and x sub n sub k are both going to be contained in a sub big N and b sub big N, because we know that both of these are going to be contained in a sub j to b sub j and a sub k to b sub k, and since those values are bigger than or equal to big N, we know that those intervals are going to be contained in each other, right? Thus, the distance between x sub n sub j and x sub n sub k is less than or equal to the distance between a sub big N and b sub big N, which is less than epsilon. So x sub n sub k is a Cauchy sequence, and thus x sub n sub k converges. The last step of the proof would be to show that L is actually contained in this interval, as we claimed in the start of the proof. Since limits preserve, what should I say? Non-strict inequalities. And this is a fact that we've already run into multiple times. So, for instance, we know x sub n is always less than or equal to m, and therefore, and so this would imply that x sub n sub k is always less than or equal to m, and this implies that L is less than or equal to m. And you can say the same thing for the opposite inequality, right? Because this interval is just defined on an inequality. And again, if you are still unsure of this fact, you would prove it by contradiction. You would assume that the limit is bigger than m, and then get a contradiction from there. Okay, so that is the proof of the Bolzano-Weierstrass theorem. The next theorem is the nested intervals theorem, which states that suppose that we have a chain of closed intervals that are nested in each other, right? So we have these decreasing inclusions, right? Meaning that if we have an element in any interval, then it's going to be contained in all the intervals before it, right? And suppose that the distance between a sub k and b sub k converges to 0, or yeah, that's all I have to say. Then the intersection of these closed intervals is equal to a single point set containing L, and a sub k converges to L, and b sub k also converges to L. So let's get into the proof of this. We will start with epsilon greater than 0. And we're going to use this limit here so there's some big N in the natural numbers such that n greater than or equal to big N implies that the distance between b sub n and a sub n is less than epsilon. Now notice that a sub n, or sorry, that n greater than or equal to big N also implies that a sub n is contained in the interval from a sub big N to b sub big N, right? Because clearly a sub n is contained in a sub n to b sub n, and this is going to be contained in a sub big N, b sub big N, right? Because for smaller values of the index, that's going to be the bigger interval. Thus, if j and k are bigger than big N, bigger, greater than or equal to big N, a sub j and a sub k are contained in this interval. So a sub j minus a sub k is less than or equal to the difference between a sub big N and b sub big N, which is less than epsilon, right? Because of this inequality here. So let a sub n. So we're going to denote L as the limit of the sequence a sub n. Now we're going to prove that the intersection of all these sets is the set containing L, and we'll also prove that b sub k also converges to the same L. All in. Okay, so since k greater than or equal to n implies a sub k is contained in the interval from a sub n to b sub n, is also contained in A sub n, B sub n for all n. And you can prove this essentially by contradiction, in that if you suppose L is outside of this interval, then, or is outside of this interval for some n, then you can arise a contradiction. So use contradiction. And therefore, since L is contained in all of these intervals, L is contained in the intersection by definition. Now let L prime be some other element of this intersection, and we wish to prove that L prime equals L. Then the distance between L and L prime is less than or equal to A sub k minus B sub k for all k. So L minus L prime is less than or equal to A sub big N minus B sub big N, which is less than epsilon. So L equals L prime, since epsilon is arbitrary, right? No matter what epsilon I pick, this distance is always going to be less than epsilon, and since this is a constant, I could say let epsilon be this distance, or if I were to argue that this distance were not 0, I could let epsilon equal that distance, and it would arise at a contradiction. So epsilon has to be 0, or not epsilon, but this distance has to be 0. Thus, the intersection of these intervals is in fact equal to the set containing L. And so the last thing we have to do is show that the B sub n converge to L. B sub n and L are contained in A sub n and B sub n for all n. So B sub big N minus L, this distance is less than or equal to B sub big N minus A sub big N, which is less than epsilon. So B sub n converges to L. And that completes the proof of the nested intervals theorem. And if you watch the topology videos, I believe this result can be used to I think it can be used to show compactness of closed intervals. I have to double check, but it kind of seems like that to me. So yeah, that concludes this lecture. Do you have any questions?
Okay.
All right, that's it.